All right, in this lecture, I'm going to start to talk about interactions, and I'm just going to give a general overview. In the next few lectures, we'll get more into the specifics and a little bit more into the mathematics. Previously, we said that in the lab, experimentalists can create a situation where, after setting things up, kind of like in this picture above, one can create in the experimental box, which is what we're calling this area over here, a state that always gives the same measurement number for a few things. First, the number of particles that are detected in this box. Two, the energy of each particle that's detected in the box. And three, the momentum of each particle. And we'll always find that if we looked at these relationships for each particle, that the energy of any particle squared is equal to the momentum of that particle squared plus some number, which we call as mass or mass squared. That's the overall setup. Mathematically, using the language of quantum mechanics, when you do an experiment like this, if you keep doing this experiment over and over again and getting exactly the same result, then we know that we can say that we've created an eigenstate of certain Hermitian operators, which we call, in this case, number of particle operator and energy operator or Hamiltonian operator H, and the total momentum of each particle operator called P, or P with this vector hat on top of it. And we also knew that we were an eigenstate of the sub particle divisions HPI, NPI, and PPI. This was for total, and this was for submomentum populations. The big point is that if we do this, set up the experiment identically, and then keep doing the same experiment over and over again, we know that in quantum mechanics we can actually get different results, but certain times we get exactly the same result over and over again, so that we know we're in an eigenstate of certain operators. That's in the language of quantum mechanics. We postulated that our entire QFD Hilbert space plus the operators structure that we developed over the first several lectures using pretty intuitive, I don't know about intuitive, but pretty crystal clear extrapolations of quantum mechanics and symmetry ideas. That mathematical model we created, we postulated that's the precise model for these experimental results that we see in these particle scattering experiments. Now, I told a little bit of a white lie, and for pedagogical reasons, it turns out that we oversimplified or misrepresented things a little bit. Our prior experimental findings that I mentioned are actually true if we only have one particle in our system. That if we get to create a system with these injectors where after we do a measurement, we only identify one particle, then everything we said is true. You can create a state where if you repeat the experiment over and over again, you get exactly the same results for number of particles, one in this case, and for momentum, and for energy, and you will find that the energy squared is equal to p squared plus m squared. The actual truth, though, is a little bit different when you have more than one particle. If we have a setup where we inject, say, two particles so that they collide, quote unquote, collide with one another, we find experimentally one of a few possibilities after a substantial amount of time is allowed to elapse. Now, I'm kind of nitpicking here, stating what's generally obvious, but still worth mentioning, because when you start looking at quantum mechanics, things that you thought were obvious are not so obvious. One of the biggest principles of quantum mechanics, if you have to express in words, is you can set things identically in terms of your experiment to perfection and still sometimes get different results. When you don't get that and you get exactly the same results, then you know you're in an eigenstate. So let's just say the idea of saying we're throwing two particles into the system, strictly speaking, we have to know what that means. How do we know we're throwing two particles into the system? And you actually have to define it, I think, by saying, I'm not an experimental person at all. I'm not even a physicist. I'm an orthopedic surgeon, but I like to at least, I've read a lot more on the theoretical side, but at least like to think about what the experiment should be. But the idea is that how do you know then you actually are starting with a particle here, a particle there? Well, very simple. If you turn off this injector and just keep this injector, and you have a situation where every time you measure one particle with exactly specific momentum and specific energy, and then you do the same thing, turn this one off and turn this one on, and then turn both of them on at the same time, that's probably what you have to do, is actually how you define it as now I've injected two particles into this system that individually were both eigenstates. But here are the possibilities when we've done it in this way, where we quote unquote inject two particles into the system. One is what we've mentioned before, that we might have a situation where when we do the experiment after we've done that and our detectors work, and our detectors, remember, tell us the number of clicks in one direction, what the momentum magnitude is in that direction, which gives us the total momentum vector quantity, and what the energy is, you can see a few things. One is that both particles show no change compared to when we just inject one at a time without the other. This means that basically there's been no interactions and the detectors find exactly the same NP, HPI, and PPI as we started with, um, as this quote unquote one at a time situation. So in other words, there's no interaction. Whatever you injected here is exactly what you get out. That's one possibility that you can see if you do this experiment. But if you do this experiment without changing anything else, changing the outside sendings and just looking at the detectors, sometimes you'll see a different result. And in that situation, you can also find a result where the detectors still show 2 for the number of particles. Remember, these detectors can count the number of particles in our experimental box, but they may have different energies, which sometimes I'll use E or sometimes I'll use P, but that's the same thing. They may show different energies for each of the particle subpopulations and different momentum for each of the particles that are coming out than what we started with. You start with P1 and P2, you end up with a situation where you have still 2 particles, but of different momentums than what you started with. That's another experimental fact that can happen. And then finally, we can also find a situation that if we repeat the same exact experiment, we can actually get different results each time. So that, like, let's say I do this experiment and I got P3 and P4 for my new momentums, but I might do it yet again and get P8 and P19 for my momentums and something different each time. And that's what we find experimentally, that you have a distribution of results. Finally, which is somewhat remarkable, but absolutely an experimental fact now, is that we can sometimes find that even though we started with 2 particles in our injectors, and we injected 2 particles into there, you can actually get a different number of particles. You can get a different n, like an nx4 or 3 or something different than, for example, the 2 we started with. What this means, assuming that our experiment and our theory are correct, that these are the most fundamental elementary particles of nature, this means that elementary particles can actually be created or destroyed in real world experiments. We haven't even gotten to the quantum mechanical explanation of anything right now in this lecture so far, but we know that experimental fact is that you can create or destroy particles because the particle number can change. And the other thing we always find experimentally is that no matter what kind of situation we have, this one, this one, this one, or this one, whatever the outcome of the experiment is, whenever we do the measurements, we'll always find that the total energy of the final particles that are that came out, if you add all of the, if you look at all of them and look at each of their energies and add all of them, is always equal to the initial energy. And we know the initial energy by looking at the energy of this thing with this turned off, and then the energy of this thing with this turned off. And we define that as 2 particles in a given eigenstate of initial energy. And assuming that when we set it up, we did get an eigenstate. But anyway, the point is that we always find, no matter what these outcomes are, is that the final energy of the whole situation is equal to the initial energy of the whole situation. And similarly, that the total final momentum of all the individual particles always equals the total initial momentum of the 2 particles. So that's actually the case, despite all the crazy stuff that we start finding with particle accelerators and quantum mechanics and quantum field theory. What is experimentally always still true is that energy is conserved and momentum is conserved. Again, still a little slight disclaimer, but I think these are for important things for pedagogical reasons. We're still oversimplifying things by assuming the existence of a single type of particle, which I'll just call a scalar particle. It's the one represented mathematically by our phi field. Realistic and everyday particles that are much more common, such as the electron and photon, as well as other ones like the muon, tau, and eventually quarks, will be presented in upcoming lectures. They will require mathematical objects a little bit more complicated than the scalar field. But if you understand the scalar field theory very well, you really understand QFT. And it's not a far stretch to begin to understand real particles. And we'll get to that in this lecture course, but not right now. Our mathematical model, thus far, we have developed the QFT Hilbert space and defined all the relevant operators on this Hilbert space. And we specifically postulated HQFT and solved for the eigenstates and eigenvalues. We found that these perfectly modeled non-interacting experiments for our elementary phi particle. That we've done so far. But this framework thus far does not predict any interactions like we actually see in the lab at all. And by interaction, I just mean a situation like we've talked about where we get something different than what we started with. We'll need to figure out a way to adjust our model to model this, what we're actually seeing in experiments for interactions. But first, I want to recall some quantum dynamics. Some of this was mentioned in the very first lecture. I'll repeat most of the big points again and maybe add a little bit more. And you're welcome to also learn about quantum dynamics and quantum mechanics textbooks. Remember, in quantum mechanics, for any quantum system, we have the following rules explaining how that system evolves in time. At any given time, for example, t sub 0, the quantum system is represented by a single vector in a Hilbert space. Here I wrote psi, and this is the time of t sub 0. This vector, which we also call a ket in our Hilbert space, can change as time evolves, ultimately becoming a new vector at a later time, t sub f. So you start with this vector in your Hilbert space, but something happens as time changes, and at a different time, the whole state of the system can be represented by this different ket or vector at psi sub tf. What determines how this thing changes? According to quantum mechanics, it's the Schrodinger equation. And the Schrodinger equation, the key part of it is the Hamiltonian. The Hamiltonian operator H, which is really the energy operator, also completely determines the evolution in time of the system. And it does it according to this, the Schrodinger equation, which you should hopefully all be familiar with from undergraduate quantum mechanics. And that's restated here in units, of course, where H bar is equal to 1. If H is not a function of time, the Hamiltonian is just always going to be the same, which in general we're going to do in QFT with some exception of some very abrupt changes. If H is not a function of time, we can solve the Schrodinger equation to get this. We can find that if you throw in any initial time t sub 0 and what the state is, and you want to know what the state is at some finite later time t sub f, you can just hit that with this operator here, which is an exponential of, so e to the minus I h, the Hamiltonian, times the time difference, tf minus t sub 0. And this is shown in standard quantum mechanics as the solution of the Schrodinger equation when you have a time-independent Hamiltonian. So this is how you do it. This something is sometimes they're called a propagator in some books, but I don't want to use that term because a propagator means something much more different and powerful in QFT. But this thing here is like an operator, which is usually symbolized by U, that will automatically take it from here to there in this relatively simple form, assuming the Hamiltonian has no time dependence. Now, if you look at this carefully and just try to think about what things mean, and whenever you do physics, you should look at an equation, slow down, and try to think what every term in it means and make sure that it makes sense, that physically everything is defined, mathematically it's defined, that you have similar mathematical objects on one side of an equation than another. You can't have two objects not, you can't have one object here and another object here and say that they're equal. Just make sure you understand what things mean. And if you look at that, you should know this from quantum mechanics, but you may just wonder again, what does the exponential of an operator mean, which is what we have here. And all it means is this, the exponential function can always be expanded like that, even for numerical values, and you extrapolate that idea to operators, and that defines what this is. So e to some operator O is just is 1, or the identity, plus operator squared over 2 factorial plus operator squared over 3 factorial, and so on and so forth. And these are now well defined because you have an operator squared, and an operator squared just means operator times the operator. And now all of this is a well-defined operator if you add the whole thing together. So that's what explains this expression. The other thing to remember from quantum dynamics is that if you start in an eigenstate of the Hamiltonian, like let's say your starting state right over here, psi t sub 0 is an eigenstate of the Hamiltonian, let's just call it E. Then if you do this expression over here, e to the minus IH tf minus d0 acting on your initial state to find out what your final state is, you will actually get the same thing back, the same final state, but now just multiplied by a number. This h turns into a number e, which is the energy of this thing, and this whole thing is just a number, a complex number. But so it basically takes you, remember in quantum mechanics, if you just have a state and multiply it by some number, you essentially get the same physical state back. This is just a different way of normalizing it. In this case, this thing has a unit modulus of 1. It's just a complex number, e to the I theta form. So this H becomes an E, and this is just shown in any standard quantum mechanics book. I think I showed that a little bit in our very first lecture, why that's true, but you can look it up almost anywhere. So if you start, the whole point is if you start in a eigenstate and you just hit it with the standard Hamiltonian, the state never changes. It's only multiplied physically by a phase factor of this form, which effectively does not change the state. So nothing ever changes. You start in an eigenstate and you just hit it with H. If as long as H is the same, then you just still end up with the same type of thing. Nothing changes. Now, in contrast, if we start off in a state at a given time t sub 0 psi, and this psi is not an eigenstate of H, and you still hit it with this to see its evolution, there will definitely be a real change in the state as time progresses. So if this thing starts off not in an eigenstate of H, and you just hit it with this thing, you are going to get a different state, which is not just a multiple of the original state, it's some combination of other states. So then there's real change. This is from quantum mechanics. So one way to get change in our system, which is ultimately what we're trying to model now in this lecture, remember we said that when you actually do experiments, you see interactions, which means that the initial state changes to something different. And we want to try to model that. So one way that we saw in regular quantum mechanics is that you start in an initial state that's not a Hamiltonian. It turns out our initial states will be an eigenstate of the Hamiltonian. So then how do you find change, which is what we want to see mathematically to represent what's going to happen in the real QFT world? Another way to potentially set things up is the following. Suppose instead of changing initial state to a different state, suppose you change the Hamiltonian. So let's just say you start with an initial Hamiltonian, which we'll now call H sub 0, which is sitting like this. And then suddenly, somehow, you change the Hamiltonian. You change the environment of the system. So there's a new Hamiltonian, which is the original one, plus some other operator, which you can regard as quote unquote small, H0 plus H sub I. And then afterwards, maybe you'll stop again and go back to the original one. But this is the key jump over here. Let's say you did that. Well, now think about what happens. If you start in an initial state of this Hamiltonian, so the initial Hamiltonian, let's say here is H sub 0, and let's say you start in an initial eigenstate of this Hamiltonian, let's just call it E, superscript 0, and some particular eigenstate of this. Remember, there could be several. That's what the subscript I is. Well, if you start in this straight state psi, from this time, minus infinity to t sub 0, this psi won't change. It'll have that phase change, but effectively it won't change. It'll just be sitting at psi, 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 because it's an eigenstate of this Hamiltonian H0. However, if you start keeping it psi, 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 psi here, as soon as you hit here, now it will evolve according to the Schrodinger equation, but the Hamiltonian that's going to make it evolve is no longer H0, it's H0 plus H sub I. So this state psi that was an eigenstate here all along suddenly is not an eigenstate of this Hamiltonian, and this will force this state psi to have a real change. It will no longer stay as psi, it'll split into some other state, and that other state in general can be expressed in any basis, but can certainly be expressed as a sum of other eigenbases, which we'll get to in a moment. But it changes is the point I want to make right now. Very important point. Now we have, in this particular setup, we have found a way that if we started in a given eigenstate of H0, it stays the same, but then suddenly changes and will evolve to something different. Now, how do you express what it evolves to something different? Because now the Hamiltonian here at these particular times is not H0, it's H0 plus H sub I. So the first question is, do we have to change our whole basis vectors? Do we have to remember our basis vectors might have been here, the eigenbasis of H0, but now we have a new Hamiltonian. Do we have to switch our eigenbasis? The answer is no, and this part gets very confusing, and it's very important to emphasize because it's confused me in the past. The underlying Hilbert space never changes when we do something like this. We're going to get to QFT in a moment. We'll see we have the same setup. The underlying Hilbert space that we define never changes. The Hamiltonian can do whatever it wants and suddenly change in time, but our mathematical arena, our underlying Hilbert space, never changes. So if we have an underlying Hilbert space, and there's a specific basis that by chance happens to be an eigenbasis of h sub 0, even though you're here, you can still say that the Hilbert space is still the same here, and you can use the same eigenbasis you did in the beginning, even though the Hamiltonian is different. You don't have to jump to the eigenbasis of this new Hamiltonian. You can use the same one here to express your results. That part's important. So for example, let's say we're going back to example, we have psi, 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 nothing changes, then something happens, and then we get a new psi, and after a certain amount of time, it'll be a new ket, which we'll call psi t sub f. That can still be expressed as a linear combination of our basis of h0. Remember, when we started, we just had an eigenstate here, so we just had one of these things. Now it got changed, but even with this change, we can still express this new state in terms of the eigenbasis here. So that's I express it over here, E0 plus E1 plus E2, where each of these are eigenstates of the original Hamiltonian H naught, even though at TF we're not at a in Hamiltonian like this. And there's some, of course, alpha, which reflects the coefficients of each of these components. Now let's go back, apply these ideas to quantum field theory. Recall that in quantum field theory so far we have been dealing with what we call Fock states. And Fock states are things like this. One particle of momentum P1 and two particles, let's say momentum P2, etc. There any state that we've talked about that could be created by acting on the vacuum state with A daggers, A dagger P's. And here we acted on with an A dagger P1 once and an A dagger P2 twice. And any state like that is called a Fock state, and that's generally the states we've been dealing with. And the beauty and the importance of the Fock states are they are eigenstates of the Hamiltonian that we've used so far, which we called HQFT. I'm going to slightly change the name in anticipation of what's just about to happen. In a little bit, we're going to find a new Hamiltonian that kicks into our system in QFT. But the Hamiltonian we've been using so far, instead of it just calling H or HQFT, I'm now just going to specifically call it H sub 0, 0 meaning no interactions. And that's what we've dealing with so far. And by definition, of course, that's this one here, 1/2 of what we've talked about a lot, the pi squared plus del phi quantity squared dot product plus m squared phi squared. Now, I don't want to bog you down too much. Sometimes if we get very technically correct, we confuse people, and this is supposed to be our first real pass at quantum field theory, our QFT1 course. We'll keep ramping it up. We're going to try to re-express a lot of our ideas in QFT2 and revisit some of these ideas with more precision, but for the most part, we've been pretty rigorous so far. The one thing I'll just mention, because you'll see it in very good books or lecture notes like David Tong's, which are phenomenal, is that in order to be consistent with the theory of special relativity, which we developed our theory showing that we have to be consistent with that, we sometimes have to normalize our states appropriately. Remember, I said that you get the same physical state even if you multiply it by a constant number in front of it. So we get to pick what number we want, and it turns out if you want to be consistent with changing frames of references in special relativity, you actually have to multiply this stuff by the correct number. I'm not going to get into why. It just takes us way off on a tangent we don't need to get into right now. We'll talk a lot more about special relativity as we get further in things. But all I'll say is that just know this, that if you look at David Tong, he gives some better explanation, but still you need to think about it a lot more as to why. That we said that our state of having two particles, one of momentum P1 and the other momentum P2, we can take the ground state and hit it with A dagger P1, A dagger P2, where I put this vector sign over it. Technically, what you have to do if you want to have consistency with other inertial frames of reference, you have to actually normalize this whole thing, if you're talking about real particles, by multiplying this by, remember, we're allowed to multiply any state by numbers, but to be consistent with special relativity and everything else, you need to actually normalize this by multiplying it by the square root of 2 times omega P1, which is this is the energy of the state P1. And then the same factor for this here, square root of 2 omega P2, and then the rest of it's still the same. It still gives you the same physical state, you just multiply it by a number, and this is the number you have to multiply it by, etc. If you have other P3, this should be P3. If you have this twice, you should see two components of this, two factors of this, so on and so forth. That's just to be consistent. So we don't have to get bogged down in this. Sometimes we do a kind of subtle thing with the nomenclature. David Tong does it, and some other books do this too, where we, instead of going back correcting any mistakes, we sometimes just do this, that if we have a vector hat over P1 and P2, that just means this state here was created using these A daggers without normalizing anything. And then when we hit it with what you're supposed to normalize it with, then we write the same state over here, and then we just omit the 3D vector notation over here. It's kind of a weird notation, but it just allows us to move forward without getting bogged down in this nonsense. Sometimes I forget to write the vectors, so just please, hopefully the point will be very clear, and the details you can look at yourself. Another thing that's sometimes done is similarly like this, which we might also do, is that if we use a dagger P1 with the 3D vector notation over the P1, we mean what we've always meant. But if we somehow don't put the vector over this, what we actually mean is we still use the a dagger P, and then we automatically build in that normalization constant here, the square root of 2 omega P. Don't worry too much about this, but this is just if you want to be consistent with special relativity, it's important. I just kind of put that up over here. That was an aside. But now let's get back to what we really wanted to look at, this QFT business of initiating change in our state. So according to quantum mechanics, which QFT also completely follows, we haven't really deviated from that at all. If we start in a state like this, and if H remains the same, if it just stays as this H0, which here I've written as this way in terms of the A daggers and APs, then we will never change the state and we'll always be like this. That's the situation we talked about last lecture. But this doesn't explain what happens in a real particle accelerator, where if you have more than one particle, things can interact, and sometimes you'll see a different state than what you started with. So that doesn't help us. So this is our situation just before we get to it again. This is the same thing that I talked about in quantum mechanics now applied to our QFT model, which is really just quantum mechanics of multiple voxels. At time t sub 0, let's just say you have some initial state here. I have three things floating around, P1, P2, and P2 again. And remember, you can, if you want, go way back to our picture of balls on 1D tracks, and everything is a ball on a 1D track. But what we regard as just a momentum state P1 of one particle is really just a bunch of different configurations of the balls, with the potential superposition of each configuration of balls. If you want to think about it like that, just to show that everything is still consistent. But that's our initial situation. And then if we don't do anything different and we just hit it with H0, where this whole thing is an eigenstate of H0, that's what we've spent previous lecture showing. And then since it's an eigenstate, nothing changes. We get back exactly the same physical state, plus or minus this phase factor, but the same physical state, it comes back. And it's obviously exactly the same if you're following along in terms of configuration space, which is more physically intuitive, but probably harder mathematically to deal with, then you still get exactly the same thing. There's no change in state. Now for interactions, here's what we do. We assume that we inject these two things into the detector. And before we inject them, let's just say when they're hanging out inside the injector here, and this one's hanging out inside the injector here, we almost just ignore this physical space, and we just think of this space and this space as some massive set of voxels, which, they're physically separated, just form one big quantum mechanic system that has a bunch of voxels. And at that time, before these physically are introduced into the actual experimental collision chamber, experimental area, we just assume that H0 is what we know it so far, the standard one without interactions, which you can express either way. But let's just say express it here as the A dagger P, AP times omega P. So before these things are actually introduced here in the lab, we just assume the whole system is living. This and this are not touching. They're actually living in the same thing we've talked about before, the same Hilbert space. Like you had all the voxels in this space, all the voxels in this space, just put them next to each other, ignore everything going on in here, and just that's the usual stuff. We get a space of two particles, a state of two particles. However, we assume that as soon as these things get introduced over here, which we'll call T sub 0 in the lab, an interaction suddenly turns on. Like once this thing gets in here, once thing comes here and they come in the collision chamber, an interaction suddenly turns on. And what we are postulating is the correct situation to represent what's happening physically is that the Hamiltonian changes. From this Hamiltonian, which we're now calling H0, meaning no interactions, it suddenly changes to a new H, which I'll just call H, And that's a combination of the original H plus some new term H sub I, which in general we quote unquote consider small. Now, for the reasons we just talked about before in quantum mechanics, we started in an eigenstate of H0, but if you suddenly at a new time change the Hamiltonian and you're in this eigenstate of H0 and then the Hamiltonian changes, now this thing is going to evolve. This thing is not an eigenstate of H, it's an eigenstate of H0. So now you will get change. And as time evolves, you'll get some brand new state, which is not the original state, which is what we're looking for. That's what we see in real life experiments in the lab. Since our underlying QFT Hilbert space never changes, we can express psi. So one way we can express, how we can express the state is indicated on this slide over here. That now in QFT, our final state, psi of t sub f, can be expressed as a new state different than what we started. Remember, we started in some eigenstate, like we might have started in this particular eigenstate over here. The Hamiltonian changed according to our postulate. When the particles get close, suddenly the Hamiltonian of the entire QFT system that we've talked about changes just by postulating that. And then that forces a change in psi. And that change in psi is a new psi, but the underlying Hilbert space, as we've mentioned, never changes. So if you had a basis for your underlying Hilbert space to begin with, whatever the psi is right now, you can still express it in terms of that basis. So technically, none of these are the eigenstates of the interaction Hamiltonian, but we can express this still as just in our Fock basis. So we can say that we could just list all of the elements of our Fock basis, which are enormous. You have a ground state, you have a state of a single particle P1, a state of a single particle P2, and all the possible momentums here, and 2 particles, and 3 particles, and 4 particles, et cetera, till a million particles. But in principle, you can express our final state as some sort of linear combination of all of these. Just following quantum mechanics and knowing that these are all bases. If you look at all of these as the basis for our whole Hilbert space. So now we're getting much closer to what we want, and I'll show you why. So we see that the interaction causes a change from an initial state. Remember, this was roughly about our initial state, something like this over here, that just had 2 particles of very well-defined momentum, P1 and P2, to all of a sudden now we have a mathematical model that creates a new state, which is now a superposition of states representing all sorts of things. You have a superposition of something that's the ground state where there's no particles, and there's some probability of that happening, alpha, to a state of 1 particle, P1, to a state of another particle, 1 particle, but just a momentum P2, to a state of 2 particles, like we started with, let's just say P1 and P2 that we just started with, to a superposition of 2 particles but of different momenta, to multiple particles, anything that's really in the Fock basis. So it's very interesting. We just created a situation where there's now a superposition. Now it becomes a lot easier to understand what this means physically, because just like in quantum mechanics, just like in ordinary quantum mechanics, when we measure now the system and this particular state right over here, we will find if we repeat the measurement over and over and over and over again of exactly this state, which was created by this physical situation, which we could identically reproduce in the lab, we will get different results each time. We might get this result, null particles. We might get this result, 1 particle, momentum P1. We might get this result, nothing changed, same original 2 particles, momentum P1 and P2. We might get this result, or we get different momenta, but still 2 particles. We may get more particles. And that's it. And what's the probability? Well, according to quantum mechanics, just whatever these alpha are. The chance of finding this result is this coefficient, modulus squared. It's just according to standard quantum mechanics right over here. Chance of finding this result is this coefficient, whatever that complex number is, take its modulus and square it, etc. This is just now quantum mechanics. So very interesting. We've now added to our mathematical model a way of representing what's really going on in the lab. In pictures, just to make sure everybody's clear, is we started with our same initial state, which we talked about before, different ways of modeling it like this. Or if you really like going back to the configuration basis, then think of the balls on the 1D track. This is some sort of superposition of balls on 1D track. And this was created by definition. Let's say it's this state of 1 P1 and 2 P2s going up. We can use the ground state, A dagger P1 and A dagger P2 hit twice, and that will give us this initial state over here, which is an eigenstate of H0. But then now all of a sudden, the state will evolve or change because our eigenstate is no longer, our Hamiltonian is no longer H0, it's H, which is H0 plus HI. And that's going to cause an evolution of the system to something different, which is now going to be some combination of Fock states. And the Fock states represent everything. It represents what we started with, plus potentially this situation here where you have, three particles, but one going this way and one going this way and one going that way, or you have, three particles but going this way. And you can, if you want, keep messing around with the configuration spaces, or just kind of remember that's the underlying thing that makes everything mathematically well defined. But you can hang out now in this line if you want. But our final state is just basically a sum of all of this. And I know I just keep hammering home the point, but it's important to get an intuitive feel. The initial state, which was P1 and two P2s, was an eigenstate of H0, but it's not an eigenstate of H. This will induce a change in the initial state to a new state. The new state will in general be a superposition of eigenstates of the original H0 as expressed here. A few remarks. Once our interaction is done, in the real world, the particles leave the experimental box and then enter the detectors. But sometimes if you start thinking about this, you can get some difficult, confusing thoughts in your head. We still assume that our QFT Hilbert space, even though particles are coming from injectors to the collision chamber back to detectors, we still assume that our QFT Hilbert space is identical throughout the entire experiment created by those voxels. The particular state, i.e. the particular ket in our Hilbert space, is what changes. The way to think of this is if our detectors can peer into the box and tell us of when they're in the language of detectors, when they're way out over here, instead of saying, all right, this thing is out in the detector, and now we're doing something else with the particle, just think of these things as a detector for this experimental box. And it's like you push a button, it tells you how many particles there are and what's the momentum of each particle and what's the energy of each particle, even though the particles physically may be going over here. But think of it like that. That's the most consistent way to actually think of quantum mechanics in general. It's a set of detectors that tells you what's happening in your experimental space. The other question is, how long exactly is this interaction time, like in this collision chamber? Do we have any way of estimating that? That's actually a difficult question to answer. And it turns out that we're actually going to ultimately assume that it's infinite. We'll get to this as time goes on. So the amount of time that this is interacting is actually going to assume to be infinity, but this is kind of infinity. This is infinity. It's almost like you have an infinity within an infinity. Infinities are very weird. You can do all sorts of weird things that sometimes don't even make any sense, but this is just how it's going to be done. When we do this, we'll find that we'll actually reach a mathematically definite answer, which matches experiment really well. So if we plug this in time of interaction as infinity, and we crank out the math, which we'll do in the next few lectures, we're going to find out that we kind of hit an equilibrium answer. And that answer also happens to be what we see in experiment to extraordinary precision. So that's why we justify it. Now, what exactly is HI? We're just talking about we're going to change the Hamiltonian into something new, H0 plus HI, but what is HI? Well, this is interesting. So we have, first of all, that just to make sure the question is well posed with a well-defined answer, recall that we have several well-defined operators on our well-defined QFT Hilbert space. Going back to our earlier lectures, I was always bothered when I studied quantum mechanics that ideas sometimes came out of nowhere. And after some time, I realized you can very precisely create quantum field theory out of just quantum mechanics ideas of multiple voxels. And that's where we got this well-defined stuff that we keep emphasizing. But anyway, we've added a new operator, HI. Everything else was nicely defined. So we have to make sure this new operator, HI, is well-defined because we have to express it in terms of any of the other well-defined operators we know. And remember, in scalar field theory, which admittedly is still kind of a toy model, it gives us huge insights into things, and we'll modify it in a little bit of time as we continue in QFT1 to represent real things like electrons and photons. But in QFT1, in scalar field theory so far, there are usually two different choices for the interaction that one encounters in textbook and lecture notes. And we're just going to pick one of them. But one of the classic ones you'll see for HI, this is really technically for the Hamiltonian density I, is some phi third factor, that you take the phi operator, which is very well defined. We know we've talked about that over and over again in the earlier lectures, and you multiply and you raise it to the third power. I mean, you do phi times phi times phi, and you multiply it by some constant, which you sometimes will call g over this funny number 3 factorial. And there's reasons we'll get to later on why we put this factorial number there. It makes things easier later on for mathematics and diagrams and things like that. That's one choice. This is called phi-third theory, I think, in some books. My favorite, as an aside book on QFT, that I read a lot of books on QFT, a lot of parts of different books, and a lot of entire books. And there's many good books, many good choices. But probably one of the mathematically best and physically best that I've come across is actually Srednicki. He's very careful with what he's saying and how he develops the theory. Um, some of it, unfortunately, starts with path integral, which we'll get to in QFT2. So that kind of takes us to a higher level than starting off. But anyway, there's a lot of good books, but he tends to use phi-third. We'll get to these later on. Right now, at this level, I have several favorite books at this very early level. David Tong is probably one of my favorites, just QFT lecture notes. He develops the theory very consistently. He's a true master. Klauber has some wonderful explicit pedagogical things and explicit examples, which makes it very easy to follow. Schwichtenberger, which is a newer book I've read most of, is also very nice for early level QFT. And right now we're going to kind of hang out here at this level. We'll build up to these things if you continue to hang out in this course. But anyway, these are two examples of HIs. Right now we're going to kind of focus on this one. We probably won't get to this one anytime soon. You can if you want, but this is the phi-4 model. And we call this constant lambda, and then we put this factor of 4 factorial for later reasons, which we'll probably show. That makes things easier when we get to something called Feynman rules. For QFT1, we'll choose the latter, which is what I said. This number, lambda, we'll just basically assume is some fraction, meaning it's between 0 and 1, so that if you square it or cube it or raise it to the 4th power, it just keeps getting smaller. This will allow us to do something called perturbation theory, so that's why we use that there, and we assume it's between 0 and 1, in general, relatively small, closer to 0. So here is our phi-4 theory. We basically say that we take our original Hamiltonian, which is this formula here. Remember, we have to integrate it over space because this is really the Hamiltonian density. And that's how we get this. This is our H0 that we've talked about all day long. To now we add this interaction term, which is this phi-4 term. And I didn't put in the, apologize, I didn't put in the lambda or the 4 factorial, but there it is for you there. But we have to still integrate that with respect to all of space. And this whole thing is called HI. It's the phi-4. This is still very well defined because this phi, as we talked about, has a very clear definition. And that's what I talked about over here. So I'll get to this. QFT1, this is now an important point. I would argue that everything we've said in our lecture course so far is a pretty solid, robust set of logical arguments. You have to believe quantum mechanics is correct. I think we have over a century of data showing that. It's probably the most well-tested idea in all of human science. And so is QFT, its offshoot. But if you just believe that's correct, and then create some sort of a model and follow through the arguments that you think apply aesthetically in terms of relativity, symmetry, locality, simplicity, things like that, we have pretty robust argument what we've done so far. We haven't done many sketchy things yet. But now is where we're going to get, in my opinion, to the real sketchy part, what we've talked about in this lecture. And this is, in my opinion, QFT1's big weakness. When we got to interactions, we said it, and I kind of sounded somewhat dramatic, that when the particle is here, and the particle is here, and it hasn't physically entered this space yet, we say it's just H0. But then when it gets into this space, this collider chamber or collision chamber, if you want to call it that, we say suddenly the whole system, which is still the same Hilbert space, still the same set of voxels, suddenly has a change in its external conditions, which changes the Hamiltonian from H0 to H0 plus H sub I. I think that's suspect, personally, and you can argue, how does that happen? Does it happen suddenly? When does that happen? All sorts of very good questions, but we just assume it happens for QFT1. When we get to QED later, you can say that's even harder to believe, because when we're here and you have an electron, it still has a charge and it still should be giving off photons. So if you have some sort of interaction between an electron and a photon, we'll get to this later, it's very hard to say the electron here is just an electron and never feels the photon until it gets here, because the electron itself can give off a photon and interact with its own photon that it just gave off. So it gets to harder to believe that, and this is a big weakness of QFT1. And when you get to ideas like renormalization, which is one of my favorite things, but we'll get to that in QFT2, we really actually can assume these things because we get into these weird infinities that would not be able to be corrected. So we can't really assume that HI is suddenly turned off when you're way out here and then turns on here. It's kind of continuously on. And then we will use tricks that are higher level math that I don't want to get to in QFT1, like Green's functions and something very important It's very poorly explained in a lot of books, but called the LSE reduction formula that we'll get to in QFT2. And this ties in with actually renormalization and things like that. But don't worry about that now. For QFT1, we'll continue the picture we showed, which again is this one here that we talked about before in the previous slide. Just a couple of comments here. The final state, of course, is a superposition of various states. As long as they're in the Fock states, that's the final superposition. That's a basis, and we can say that there's always this one thing which is a particular Fock state. Because of the interaction, now it changes to a superposition of all Fock states in principle with some coefficients. I wrote A1 instead of alpha 1. What's interesting, if you look at these, obviously, it's very obvious from our formalism, but if you start looking as an experimentalist, it's kind of dramatic what we're predicting if you didn't know about it already from the lab, is that you can start with a particle of two states, and very naturally you have a particle of a system now of three states. You created an elementary particle. Here you created three states, or you can create five states, or you can lose particles. So very easily, remember in quantum mechanics, you start with one electron or two electrons, and you have a Hamiltonian, and then you can do everything you want to see how it evolves with time, but it'll never change from two electrons to three electrons to one electrons. This is nicely brought up in Z's book, which is another very good, intuitive, and fun book. But one electron will always stay one electron, two electrons will always stay two electrons. You don't have any formalism in quantum mechanics to suddenly change particle number. Here, very naturally, without violating anything in actually the underlying principles of quantum mechanics, we have a correct model that will allow us to change particle numbers. We can create and destroy particles easily. What's happening? Well, what are you creating and destroying? Are you really changing your underlying system? No. Nature itself is not made out of elementary particles. It's made out of voxels. And in the scalar field theory, it's 1D track and a ball moving up and down this 1D track in each voxel. And you can just mess or tinker with all these different voxels and get no particles, or you get one particle by messing with the voxels, but the ball on the 1D track in this voxel, this voxel, this voxel, this voxel, and so on in different voxels, and add the superpositions. You can just tinker with the balls on the 1D track at different voxels and get different states, especially if you take their superposition. You easily will get what experimentalists see as two particles, but really for you, you're just messing with voxels. You're not creating or destroying voxels. Those are the fundamental units of nature. In that regard, that I'm throwing out some wild ideas here, but potentially you can say conservation of voxel number, not of elementary particles. And that's it.